Our third gas law is Boyle's law, which tells us that volume and pressure are inversely proportional. So as one goes up, the other goes down. This is the only one of our four individual gas laws that has an inverse proportionality. We could write our equation as pressure is proportional to 1 over volume, or we could say pressure is equal to some constant times 1 over volume. This equation is true in a variety of different circumstances. So pressure 1 equals constant times 1 over volume 1, and pressure 2 equals constant times 1 over volume 2. We could set those constants equal to each other and end up with P1 times V1 equals P2 times V2. Because of the inverse proportionality, this is the only equation that looks like a multiplication problem rather than a division problem, at least before rearranging. As with our first two gas laws, pressure and volume do not have specific units required, as long as they are consistent on both sides of the equation. We can graph Boyle's law data, but if we were to graph pressure versus volume, we would get a curve that is not a straight line. What you'll notice on the top graph is that as the pressure increases, the volume decreases. As the volume increases, the pressure decreases. Because of the inverse proportionality, if we want a straight line, we need to graph 1 over pressure versus volume, or pressure versus 1 over volume, to get a straight line. Just like with all our other individual gas laws, we are making some assumptions. Since we're varying volume and pressure, moles and temperature are being held constant. Boyle's law is important for a lot of different things, including breathing. When you breathe in, your diaphragm contracts, expanding the lungs. Because the lungs have a larger volume, the pressure inside the lungs drops. The smaller pressure inside the lungs compared to the outside pressure means that air is going to flow into the lungs, so you breathe in. Then, when you're trying to breathe out, the diaphragm relaxes, which pushes the lungs smaller again. With that smaller volume, the pressure is increased, forcing the air out of the lungs. Here's an example using Boyle's law to do a calculation. We have a gas that has a volume of 15 milliliters and a pressure of 13 psi. We want to find the new pressure when the volume is 7.5 milliliters. Our V1 is 15 milliliters. Again, with pressures and volumes, it doesn't really matter what our units are, as long as we're consistent. We can leave it in milliliters. P1 is 13 psi. V2 is 7.5 milliliters. We're using the Boyle's law equation, P1V1 equals P2V2. But before we plug in our values, we need to get the variable we're solving for by itself on one side of the equal sign. We're trying to find the new pressure, P2. So to get it by itself, we divide both sides by V2. Our rearranged equation is P2 equals P1 times V1 divided by V2. We plug in our values in the correct spots and come out with 26 psi. This answer should make sense. We're cutting our volume in half, so we expect our pressure to double, and it does. Our fourth gas law is Avogadro's law, which tells us that volume and moles are directly proportional. As moles go up, the volume also goes up. We can again express this as a before and after set of equations. V1 over N1 equals V2 over N2. With Avogadro's law, we may do some calculations like that, but we'll also do some different calculations based on the concept of Avogadro's law. Let's talk about the concept a little bit. Remember, in our balanced chemical equations, the coefficients tell us the ratios of moles in the reaction or the ratios of molecules in the reaction. 3 moles of H2 reacts with 1 mole of N2 to make 2 moles of NH3, or we could say the same thing with molecules. Now we can add another aspect. Since volume and moles are directly proportional, we can also use our coefficients with relationship to volumes. For example, we could say 3 volumes of H2 gas reacts with 1 volume of N2 gas to make 2 volumes of ammonia gas. Keep in mind, this is only true for gases. It cannot be assumed for volumes of solids or liquids or aqueous solutions. This concept can be useful for predicting what volume the products of a reaction will take up. On the left side of the arrow in this equation, there are a total of 4 boxes representing 4 volumes, whereas on the right side of the arrow, there are 2 boxes representing 2 volumes. The volume is getting smaller over the course of the reaction. Let's say this was happening in a balloon. The balloon should shrink because the number of moles at the end is fewer. I like to think of molecules as Amazon boxes. They're going to be all essentially the same size. They may contain different things, just like you could have a plate or a lamp or an alarm clock fitting in the same size box. The volumes of each molecule are going to be treated as if they're all the same size, regardless of what type of molecule it is.